Ever wondered how robots really make sense of the chaotic, three-dimensional world around them? Or how virtual environments could feel truly lifelike? Today, we're exploring a breakthrough study that's transforming how AI and robotics interact with real-world 3D data. Let's unpack how researchers are turning messy, real-world scans into tools for smarter machines and more immersive digital experiences. So what's the big deal with 3D scans? Imagine capturing an entire room in hyper-detailed 3D, every chair, table, and wall, down to the texture of the floor. These scans are incredibly realistic, but they're also massive, inconsistent, and hard to process. Think of them as a puzzle with missing pieces and irregular shapes. Traditional AI systems struggle to parse this complexity, which is why most robotics and simulation tools rely on synthetic data, computer-generated scenes that are clean but lack the unpredictability of real environments. But here's the problem: synthetic data is like a dollhouse. It's perfect, but it doesn't capture the chaos of the real world. This research is changing that by using real 3D scans, like those from the ScanNet++ dataset, and finding ways to make them work with AI and robotics. The key innovation: a format called USD, the Universal Scene Description. Think of USD as a universal language for 3D scenes. It's like a blueprint that can adapt to different needs. The team created two versions, one for semantic understanding, where objects are labeled and organized, and another for geometry-focused tasks like physics simulations. Let's say you want to teach a robot to tidy a room. The robot needs to know where a mug goes, on a table, not the floor. The researchers used USD to label every object and its parts, then fed that into an AI. The AI, like a large language model, LLM, figured out where to place a new object based on context. Want to add a lamp? The system suggests placing it on a desk, not a couch. And guess what? This worked 80% of the time, without needing to retrain the AI from scratch. Now let's talk robots. Simulating real-world environments is tricky. Real scans have gaps, weird shapes, and inconsistent data. The team tackled this by simplifying the 3D meshes, like trimming extra details, and fixing issues like objects falling through the floor. They even made sure robots could learn from these scans, achieving 87% success in tasks like picking up objects. Why does this matter? Imagine robots that can navigate your home without glitching, or virtual reality that feels exactly like a real room. This research is making that possible by turning chaotic real-world data into something AI and robots can actually use. So the next time you see a robot or a virtual world, remember, it might be powered by the messy, beautiful complexity of real-life 3D scans. Thanks for watching, stay curious, and let's keep exploring how AI is reshaping our world. But here's where the real challenge begins. The study didn't just stop at simulations. Researchers tested their system in real-world environments, and the gap between virtual and physical worlds became stark. Take object placement. While the AI nailed 80% of tasks in simulations, real-world scenarios like placing a mug on a counter revealed hidden complexities. Why? Real spaces have irregular geometries, ambiguous labels, and objects that don't always behave as expected. To tackle this, the team compared two approaches: planner-based policies and reinforcement learning, specifically PPO algorithms. Planner-based systems, which use predefined rules and logic, achieved 100% success in tasks like opening a cabinet drawer. These are like having a roadmap, every step is calculated. Meanwhile, PPO, where robots learn through trial and error, hit 87% success. The difference? Planner-based systems are deterministic, while PPO is probabilistic, making them more prone to errors in unpredictable environments. Here's the kicker: when tested in real-world environments, synthetic data, once a gold standard, fell short. Robots trained on computer-generated scenes mastered tasks like drawer opening with 98% success, but real-world cabinets posed challenges. The robot would often bypass handles entirely, grabbing the drawer from the side. By tweaking the reward system to prioritize handle use, they improved performance, but at a cost. The robot started dropping the drawer during pulls, highlighting how real-world physics and geometry are far more complex than simulations. This underscores the importance of high-quality, detailed data. The study used the Articulate3D dataset, which combines semantic annotations, what objects are, with geometric precision. By merging these layers, researchers built systems that understand context, scale, and real-world quirks. Even a simple task like placing a mug on a counter reveals deep challenges in AI, like distinguishing between a kitchen counter and a bathroom sink, where object labels and geometries are ambiguous. This work isn't just about making robots smarter. It's about creating systems that navigate the messy, unpredictable world with nuance. As we've seen, the line between virtual and physical is blurring, and the tools we build today will shape the robots of tomorrow. Thanks for watching. If you want to dive deeper into how these systems are reshaping automation, hit subscribe. And drop a comment below: what should robots learn next? Until next time, stay curious.